Okay guys, welcome to lesson 5, the effect of lenses on light. This is our last optics video. Next week we're going to start with electronics. So let's jump right into this last lesson. If you're taking notes, it is May now. I've been recording this, so this is called the effect of lenses on light. In this lesson, we are going to investigate the refraction of light through convex and concave lenses by designing tests on how to produce virtual and real images, then compare our findings to that of what we learned last week with curved mirrors. So, right off the bat, these are the two types of lenses we're going to be talking about today. The converging lens, which is convex, and the diverging lens, which is called a concave. So, let's watch a quick video on the properties of these, both virtual and real images. Okay, so let's start off by talking about the two types of lenses. The one I have in this hand is what we call a concave lens. As you can see, it's caved inward, hence the name concave. And what that does is when light, and I'll show you here in a second, when light enters it, it spreads it outward, or it diverges the rays. Now this one right here is a convex lens. Okay, and the convex is just the opposite, of course, and what happens here is it will actually converge the beams as we see them in a second. So before I show you how real images are formed by this, let me show you the type of virtual images you get from each of these. So if you have a concave lens, that lens is actually it will never form a real image, but it will form a virtual image. And the way I like to demonstrate that is if I take two of these, if you guys look at my eyes, and then I'm going to put these right in front of my eyes, you will notice my eyes just got smaller. So a concave lens will always create a virtual image that is smaller than the object. Now, here I have a larger convex lens, and this one you will notice, and I think we all have seen these before, it makes the virtual image larger. So if I put it up to my eye here, you can see I get a much larger eye. So they both form virtual images. Concave lens makes the image smaller. Convex lens makes the image larger. So now, if you guys look over here at this box I made, I have a concave lens mounted here, and I have a convex lens mounted here. I'm going to go ahead and show you what happens to light as it enters these lenses. Now, first of all, these lenses are made of glass. So as light enters glass, glass has a higher index of refraction than air, so it's going to bend the light towards the normal. But in this case, if you follow my hands, as the light goes in, the curve of the mirror it's an outward curve, so that when the light goes in, it bends towards the thicker part of the lens, right? Because it's towards the normal, and then it'll shoot out away from the lens. So if you take a look here, that's why we call this a diverging lens. So the beam comes in straight on, it just goes straight through. But now as the glass gets thicker, you can see the beam gets diverged away. It's still bending towards the normal, but in this case it's being directed outward because of the curve of the mirror, or lens. So if I take this ray box here that has the 3 slits in it, you can see as they come in, all 3 of them, the 2 on the sides get diverged out, the one dead center just keeps going straight. With the convex lens, which is converging lens, same thing happens. Light enters, light slows down, thanks to Snell's law. And then, because the angle now of the convex lens is in such a way that when the light enters, it bends it inward, right, which is still towards the normal, and then it'll all converge out here somewhere. So as I move it parallel, you can see this beam being directed inward. And here it is. Focus on this beam here. You can see it goes inward. So if I put the ray box on there, same thing happens. All 3 beams come in, and as you can see, I do a point where all 3 of these rays meet, and that would be the focal point of this lens. Now, since all the rays meet right at this focal point, if I were to take another lens, like an eye doctor would do, if you needed corrected vision, Sometimes this beam of light on your natural, your own lens in your eye, it shoots the light beyond the focal point on your retina. So what they do is they bring that focal point inward with a corrective lens, and that's where you get glasses. And you can see it corrects it by moving that up here. And suppose this is the back of your retina, now you would be able to focus in on the image. So that's what glasses do. Okay? And as you get older, sometimes you'll need to put a concave lens. We call them bifocals, so you'll have two lenses on the same glass. Okay, so hopefully that made sense. I'm just going to give you a couple quick notes here on lenses. If you choose to take them, that's great. If not, I understand. But there's two variables which determine how much light is refracted in a lens. Okay, so the first one, as you probably figured out, is the index of refraction, what that lens is made out of. Glass, of course, we found out last week, bends light more than acrylic. Right? Water also bends it. You can make a lens out of water, right? Put it in maybe a clear baggie, and suddenly you have a lens. So one, the material, the index of refraction, and two, the shape of the lens, right? You could have a really really thick-centered convex lens, and it tapers at the ends, or it could be even less shallow. All right. So shape and material. Also, concave lenses, real specific here, they are diverging lenses, and they only form virtual images. You saw in the little video clip, my eyes got really small. That was a virtual image, and it's always smaller and upright, like we learned from our last videos. And then the convex lens, those can converge, so they will form real images. They're the only type of lens that forms real images. And of course, they form virtual images that are always larger. So we're going to do a quick little activity here, which is going to compare the actual image, the image distance to the object distance. And we're going to use the mirror equation for this. So this is going to be just like the activity we did with the candle and the mirrors last couple weeks ago. But this time we're going to be using the lenses for this. One lens, a converging lens. So this is what you're going to see in the video. We're going to have an object beyond 2f. The object's going to be the candle, and we're going to put it at 60 centimeters. Notice up here, the lens has a focal point of 9 centimeters. So we're going to stick a candle 60 centimeters away from it and see the virtual image that it forms. Then we're going to do it at twice the focal point. Remember, with mirrors, with center of curvature, for lenses, we go twice the focal point because remember, there's two variables that affect how much light gets bent in a lens based on its shape and its material. So we don't use center of curvature for lenses, we use twice the focal point. So we're going to do basically the same activity we did a couple weeks ago with mirrors, but this time with lenses. And before we do that activity, we're going to actually calculate where the image will form. So this first one, beyond 2f, we're going to use di equals do times f over do minus f. And for the first one on beyond 2f, that image should form right around 10.6. We'll probably see it more closer to the actual focal point, which will be 9. At twice the focal point, just like the mirrors, we should see an image forming right at 18 centimeters. And then between 2f and f, we're going to put it at 12 centimeters. And according to this calculation, that'll come out to be 36 centimeters. Right at the focal point, there should be no image forming. And then between f and 2f, we're going to get just a virtual image. And look at that. When I did the calculation, it came out to be a negative number. So let's go ahead and watch that video now. Okay, so in this little segment, we're going to look at convex lenses, this one particular, which I've already found the focal point, which is 9 centimeters. So we're going to focus on the real image formation of a convex lens. We're going to go ahead and use the paper that I showed you in the video, the PowerPoint. We're going to put the object, which is a candle, we're going to put it beyond 2f. Since the focal point of this lens is 9 centimeters, twice that focal point is 18 centimeters. So we're going to set it way beyond that, 60 centimeters, and in our calculation it came out to be 10.6. which will probably come out to be more like 9 because that's so far away from the 2F that it's probably going to be right at the focal point. Then we're going to go at 2F, which is 2 times 9 is 18 centimeters. Then we're going to go at the focal point, or between 2F and F, which is going to be 12 centimeters. And then we'll go right at the focal point, which is 9 centimeters. And then between F and 2F, the lens, which we won't get any real image, we should get a virtual image as seen by the negative number here. So I'm not even going to take the time and write down where our image locations occur, but we'll just go ahead and prove that the lens maker equation or the mirror equation works for lenses as it did with mirrors last week. Okay, so let's start off with beyond 2F. So 9 centimeters is the focal point. Here's 9. 18 is right here. So I'm going to come all the way over here on my meter stick to 60. So right now I'm sitting right at 60. So now we're getting the light entering this lens and converging somewhere out here. And according to our paper, it should be converging right around 10.6. I'm going to assume it's going to be more like 9. So I'll put up my screen and we should be able to capture the image as I approach the 9 centimeter mark or 10 point. Yep, there it is. And look at that. We get a nice crisp image right at about 10. Okay, so I could probably scoot it back further and further and it's going to approach 9 as it goes further and further away from 2F. Okay, so that's what we expected there. Oh, and notice it is inverted, upside down, and it is smaller, so that is a real image. Remember, all real images are always inverted. Okay, so now let's go to 2F. So right at twice the focal point. So the focal point is 9. 2F would be 18. So I'm going to stick it right at 18. And remember with the mirrors, when we were at C, which is equivalent to 2F, the image formed right at the center of curvature. Well, here, the image should form right at twice the focal point. So we're at 18 centimeters there. If I bring my screen right up to 18 centimeters, there it is. Inverted, same size, all the same properties of the real images we notice with mirrors is now happening with the lens. Okay, now we go to between 2F and F. So I chose 12 centimeters. So if you remember from last week with mirrors, this is going to make the image larger. So now we're between 9 and 18, so we're right at 12. So now we should get a larger inverted real image. And according to our calculations, that would be 36 centimeters. So as we come here and approach 36, there you could see a nice, crisp, real image, and it is larger. Okay, and then at 9, right at the focal point, we're going to get a, right at 9, we're going to get a spotlight, right? There's no image formation here. So as I put it on there, you get kind of a blurry image there, but as you guys can see, right at 9, that's that nice spotlight we get, okay? And finally, the last one between F and the lens. So I'm just going to put this right at 5. And then you'll see there is no image formation here. It's all blurry. We don't get anything. But if I get my camera to walk over to the other side, we're going to see a virtual image. And that virtual image will be upright and it'll be behind the mirror. So hopefully that formation occurs. As we look into the lens, just like when you saw my eyeball larger, now you see the virtual image of the large flame.
There we go.
Okay, after seeing that video, here is all the data. I'm not going to repeat any of it, but yeah, what we predicted would happen did happen. Notice this column here. All of the real images that were formed, they were inverted. When it was beyond 2F, it was smaller. When it was between F and 2F, it was larger, right? And the same size. So same properties we saw as the mirrors. And then Back here, we never really measured how far it was behind the lens, so I didn't get a calculation there. That would have been kind of hard to do. Okay, so for this next activity, I really hope you guys will try this at home. If you look on your Google Classroom, there is an attachment which is a ray diagram of convex lenses. It looks like this. If you can print it out, that would be great. If not, you can just kind of draw them freehand in your journal. And of course, if not, just follow along my PowerPoint as I go through how to do these ray diagrams. So for this activity, you'll need a straight edge like you did for the mirrors, and 2 different colored pencils would be great. And of course, this copy of this handout. Okay, so let's jump right into it. So when you're doing ray diagrams of lenses, there's only 2 rules. So this one's a lot easier. And the first rule right here is I've highlighted it in red in every slide. Any light ray drawn parallel to the principal axis is refracted through the focal point on the other side of the lens. So let's go ahead and do that. And we're going to go right at the point of the candle and go ahead and draw a line parallel, as I did there. And then as soon as it goes through the principal axis, it will bend right through the focal point. So it goes right through the focal point. Then the second rule, any light ray drawn through the vertex, center of the lens, continues in a straight line. So check this out. It just goes right from the point, right through the vertex. And then look at that. It crosses right over here. There's my pointer. Crosses right there. So that's where our real image formation will occur. And there you have it. So it's inverted and it's smaller. Okay, and real, inverted, smaller image. Okay, at 2F. So here it is. We're going to probably see we will see the exact same thing which we saw in the activity. It's going to be the same size. Parallel through F, and then right through the vertex. They all cross and meet right there. Okay, hopefully you've tried all of these already. Let's go ahead and take a look at the other one. Oh, real, inverted, same size. Okay, between F and 2F, parallel to the focal point, right through the vertex, and we can see way over here is where they meet, and you get the larger inverted image. Okay, and it's larger. Okay. Then at F, this is where we get no image formation. This is again a spotlight. Parallel through F, straight through the vertex, and there you have the 2 parallel beams making the spotlight. Okay. Now, the virtual image, this is the one where we are going to get the light rays are going to go through, but we're going to appear to see an image over here, and it will be upright, so it'll be a parallel, or it'll be a virtual image. So, first of all, parallel through the focal point, but we're going to see that we're going to extend that line up here through because our eyeball is going to be over here. Oh, actually, let's go ahead and draw this other one through the vertex, and then we'll put the eyeball on there. And then you'll see they extend up, and they appear to cross right here. That's why it's a virtual image, and it's upright. And larger. Okay, now this one isn't on your paper, but this is a concave lens. If you want to try it, go ahead and put this on pause and try it on your own. But basically, it's the same thing I'm going to show you right now. You draw your first line parallel, then it goes up there. Remember, it diverges, but you draw the line through the focal point, as you can see right there, and that's the direction it appears to go. And then same thing here through the vertex. If you put your eye on the other side, that line that just went through the vertex appears to be crossing and forming that smaller real image. Okay, that's it for this recording, folks. Hopefully you enjoyed it. Your homework assignment this week is page 574, Physics to Go. numbers 1, 3, 4, 6, 7, 8, 9, and 11. Okay? Of those problems, 6, 7, and 8 are calculations. So here's the answers to those calculations. So check to make sure you did it right when you do those. Okay? And this is the last, like I said earlier, this is the last assignment for the optics unit on light and sound. We're not going to have a test on this stuff. We're just going to jump right into electronics next week.